This is Sung, and I'm the Principal and Director of Sky Academy. And in this episode, I really want to continue our journey through probability. And the part where I really want to focus on is sampling without replacement. We touched on it last episode, right? But this episode, I want to do sampling without replacement as it relates to large populations. All right. So basically, where you've got a large population, right? When you take a sample out, you're not really affecting the pool of what's left over as much as you were if you've got a small, finite number of items that you're taking out one from. Okay, so whereas before, when you're sampling without replacement, you're affecting the probabilities of the successive events. You're not going to do that so much with sampling without replacement for a large population. Okay, so I'll show you what that means as we do an example. That's probably the best way of doing it. So let's read this question. A manufacturer finds that 10% of the articles made in his factories are defective. Okay, so that 1 out of 10 is defective. 3 articles are taken at random. What is the probability that all are defective, none are defective, more than there are more defective samples than non-defective samples? Okay, so let's have a look at this, right? So what you've got is you've got 3 random articles, all right? 1, 2, and 3. So you've got, okay. Does that make sense? That's basically your probability tree for something like this. Now we're told that 10% are defective, which means 90% are non-defective. Does that make sense? So let's have a look here. 1 out of 10 is defective, 9 out of 10 is non-defective, right? You take this defective sample away, you don't replace it, in a large population, it's not going to affect the probability of the pool of what's left over as much as if you've got a small sample, right? So basically, before, this number would go down by 1, but with a large population, you don't worry about it. You don't worry about this missing thing and how it's going to affect the population, how it's going to affect the probability of the population. All right, so basically, you got 1 out of 10 here, all right? 1 out of 10 will be the probability of choosing another defective item, and this will be 9 out of 10 as well. All right, so with a large population, the probabilities don't change. So 1 out of 10, 9 out of 10. 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 All right, does that make sense? So the key thing that I want to say is with a large population, the fact that you don't replace doesn't affect the probabilities at all. Okay? Because the population is so large that it can deal with it. It can deal with the fact that one's been taken out. All right? The population, the pool will still be, the one that gets taken out will have a negligible impact or negligible influence on the rest of the probabilities that follow. Okay? So here we've got D, 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 N, D, N, D. Now, N, D, D, because they do get pretty tedious. But if you do know how to do them, they're the most boring and easy marks that you can get in an exam. Okay, so just practice them, alright? If only for the sake of getting the marks. So the probability of DDD, defective, 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 will be 1 out of 10 times 1 out of 10 times 1 out of 10. The probability of DDN would be 1 out of 10 times 1 out of 10 times 9 out of 10. DND would be, what would that be? 1 out of 10 times 9 out of 10 times 1 out of 10. DNN, 1 out of 10 times 9 out of 10 times 9 out of 10. NDD, 9 out of 10 times 1 out of 10 times 1 out of 10. And you can see what I'm doing, can't you? Instead of multiplying across, right, I've pretty much memorized that N is 9 out of 10 and D is 1 out of 10, right? So it's 9 out of 10 times 1 out of 10 times 1 out of 10. 9 out of 10 times 9 out of 10 times 1 out of 10. 9 out of 10 times 9 out of 10 times 9 out of 10. Now when it comes to doing these questions, all are defective. What is the probability that all are defective? All are defective. 1 out of 10 times 1 out of 10 times 1 out of 10. Now, if I did this, would you understand what I'm doing? Putting a bracket around there and putting a P in front. All right? What does that mean? It means the probability that all of the items are defective. Does that make sense? Work it out. It comes 1 out of 1,000. Okay? The next one, none are defective. NNN, probability that none defective. So what is it? 9 out of 10 times 9 out of 10 times 9 out of 10, which ends up being 729 out of 1,000, 0.729. The third one, a little bit more challenging. What do we got? More defective than non-defective. Okay, so what that's going to include, more defective than non-defective, and I'll use a red pen here. Now, which ones are we going to include? 3 defective, 0 non-defective, 2 defective, 1 non-defective. That's where we've got more defects than non-defects. This one's the same. 2 defective, 1 non-defective. This one. 1 defective, 2 non-defective. That's not going to be included. 2 defective, 1 non-defective. That's going to be included. 2 non, 1 defective. That's not included. 2 non, 1 defective. That's not included. Defective, non-defective, non-defective, non-defective. That's not going to be included. Okay. So in each of the examples where I've highlighted it or put a red star next to it, they're examples where there are more defective samples in the random. There are more defective items in the random sample than there are not. All right. So we've got to add up the probability of that, and that. Okay. So the probability where defective is greater than non-defective will be 1 out of 1,000 plus 1 times 1 is 1 times another 9 is 9 out of 1,000 plus 1 times 9 is 9 times 1 is 9 out of 1,000. And then the last one, 9 times 1 times 1, which will be 9 out of 1,000 as well. Okay? So, the probability that there are more defectives than non-defectives is 9 plus 9 plus 9, which is 27, plus 1, which is 28. 28 out of 1,000, which ends up being 0.028. Does that make sense? What I wanted to get across when doing sampling without replacement for large population is basically to let you know that the probabilities remain unaffected by the event beforehand, okay? By the outcome beforehand. So in other words, the fact that this one is defective doesn't affect the successive outcome, okay? And that's really what I wanted to come across. So you do them pretty much the same way as you would an independent case, okay? Good. Now, thank you for persevering with me on this journey through probability. I've got one more episode left, and that episode really just is a summary of everything that we've learnt to date, okay? So thank you very much for watching, and all the best with your studies for the rest of the course. Thank you.